So today we are going to continue looking at modules, and in particular, we want to look at the correspondence between vector spaces V over field F and a given linear transformation of that vector space into itself, and looking at V as an FX module. So these two are in correspondence, and today we are going to look at the right-hand side. If we have a vector space V over F, how can we extend that to a vector, a module over fx? How can we extend v to a module over fx that respects the vector space structure already given by the action of f on v? So let's fix notation. We let f be a field, x an indeterminate over f, and we let v be an f vector space. As we said, we wish to extend the f vector space structure of v to fx module structure. So that would be left fx module structure. Um, the question is, how can we do this? We will do this by means of linear transformations from v into itself. So we let t map v onto itself be any arbitrary linear transformation, and we will fix some notation that will become useful later. For any positive integer n, we didn't mean by t to the n, that's just repeated composition of t with itself. And we take t to the 0 to be equal to the identity linear transformation, and t to the 1 just to be equal to t. Now we can add linear transformations pointwise. If we have two linear transformations, a and b, that map v onto itself, and we have two scalars, or two elements of our field, alpha and beta, then we can define the sum alpha a plus beta b as for all v in our vector space v, um, alpha times a plus beta times b, all of that applied to v. That's going to essentially quote unquote distribute our v into the sum, and that would be give us alpha times a of v plus beta times b of v. So this definition, linear combination of linear transformations, is again a linear transformation. You can check that this is indeed a linear transformation, but we won't do that here. But the other important thing that will become useful later is that we can inductively prove that this holds for any number of summands. So we can take an arbitrary sum, not an infinite sum, but an arbitrary sum of finite length of linear transformations from V to itself and add them pointwise. So now we are ready to define the action of fx on V. If we recall, that is exactly what we want to do. We are given an F module V. I'm sorry, we are given an F vector space V, where F is a field, and now we have a linear transformation T that maps V onto itself. We want to somehow construct fx module, an fx module structure on V through our given linear transformation that extends our F vector space structure of V. So we let p of x be equal to this polynomial right here, a sub n x to the n plus dot 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 a sub 1 x plus a sub 0. So this is indeed a polynomial of our polynomial ring fx. For all v elements of our vector space, we define the action of p of x on v as the following. So we have p of x applied to v, and I'll denote an action, the action of fx on v with this little dot here. That's going to be equal to, so now here we see that we essentially plug in our linear transformation for x. So we have a sub n t to the n plus a sub n minus 1 t to the n minus 1 plus dot 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 a sub 1 t plus a sub 0. Now all of that is being applied to our element v. Now this application, as we've proven before, or as I gave as a definition before, that the arbitrary linear combination of linear transformations is again a linear transformation. So this indeed does make sense. And these powers are again linear transformations. And if we apply this through the sum, we just simply get a sub n t to the n applied to v plus a sub n minus 1 t to the n minus 1 applied to v plus all the way down the line to a sub 1 times t applied to v, and then we have plus a sub 0. This would actually be our zeroth term, so it would be t to the 0, but we know that t to the 0 is equal to the identity transformation. So that would just be I of v, and that would just give us v again. So we just drop the 0th term there. And now we notice too that all of these guys are is the action. So t is a linear transformation. Any power of t is a linear transformation from v to itself. And we see that a sub n, all of our a sub i's for I equal to n all the way through 0, these are elements of our field. So this is indeed actually just a linear combination of elements of v, of our vector space. So all this stuff is taking place under our vector space structure of v. Now there's a special there's a special element here, that's our polynomial x. The polynomial x acts as the linear transformation t on v. So in a sense, we're taking this action, right, the action of x on v, and extending it quote unquote linearly to all of fx. And we'd see this as follows. So the action of x on an element v in v is given by, so x acting on the left on our element v is just t of v. That's just to demonstrate that we take our structure, that we take the action of x on v to be the linear transformation, then we extend it to all other types of powers of x and linear combinations of polynomials in our polynomial ring. So our claim is that the action, this action that we just defined of fx on v on our vector space v makes our vector space v into a left fx module. We need to check the 4 module axioms are satisfied. So we will recall the definition of a left R module. So we let R, we're going to read the definition and go through it a little bit just to refresh our memories, and then we'll proceed to prove that fx, the action of fx on v, does indeed give us a left module structure. So we let R be a unitary ring by an R module, a left R module in our case. We mean an abelian group M together with the left action. So an action is essentially just a like a multivariate map. So we have R cross M. So we have a map from the product into M that can be described by, essentially we just take these two elements. So in the product, so lambda comma x in the product, and we just concatenate them and write them next to each other, lambda x. And they satisfy the 4 following properties. For all the elements of our abelian group and all elements of our ring, we have this left distribution over sums. So lambda times x plus y is equal to lambda x plus lambda y. And we have kind of like the converse for elements in our ring. So we have all elements of our ring, lambda mu, and all elements of our abelian group x. We have lambda plus mu. Applying that on the left to x is the same thing as applying lambda to x and then adding on mu applied to x. We have an associativity property, which is lambda for all lambda and mu in R and all elements of M. We have that lambda applied on the left to mu applied to x is equal to the product lambda times mu applied to x. And lastly, we have for all elements of our abelian group that the unitary element, the unit element, our multiplicative identity applied to x acts as the identity function on M. So we simply have 1 sub r applied to x is equal to x. So now we are ready to prove that the action that we gave before gives fx module structure to our vector space, our f vector space v. So we let p and q be elements of our ring, and we let v and w be elements of our vector space. Then we have the following. So we have p applied to v plus w, and if we take p of x to be what we had before, what we defined it to be before, we simply do what we did before. We follow the definition. So we substitute in all of our linear transformations, apply that to our sum. Then we take the individual linear transformations and apply them to our sum v plus w. And then since the powers of linear transformations are the powers or the repeated decomposition of linear transformations from v to itself is again a linear transformation, we can simply just essentially factor out v plus w. So we get t to the n of v plus dot 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 a sub 0 plus a sub n, t to the n applied to w plus dot 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 a sub 1, t to the w plus a sub 0 applied to w, and that is just the same as p of x applied to v plus p of x applied to w. And that shows that we have our left distributive property. Next, if we take sums in our ring first and then apply them to an element v of our vector space v, um, we simply get their sum is just going to be the two polynomials essentially written right next to each other. We don't even have to reorder data terms or anything. We just write them next to each other. We swap in our linear transformations. We apply that to v, and then we write them again as a separate sum. So this is a pretty straightforward part. There's no reordering of the terms or anything. We just write them next to each other, apply each linear transformation individually to v, and then write them separately again. Now the constant polynomial 1 acts trivially, since if we have the constant polynomial 1 applied to v, that's going to be equal to just how we have here in our constant terms. It's just going to be the action of 1 in our f vector space v. That's going to be 1 applied to v, which is going to be equal to v, not 1. That was an accident. And that's just from the action of f on v. And the last thing we need to check is multiplication. So we need to check that our multiplication is associative. This follows a similar flavor to what we've done so far, so I'll leave that as an exercise. Now we can view f as a subring of fx, and the action of f on v, viewing v as an f vector space, is precisely the same as the action of f when viewed as a subset of fx. So in this way, the action of fx is consistent with the given action of f on v, and we see that this definition does indeed extend the action of f on v to an action of fx on v. So essentially all that we're saying is that if we look at v with f vector space structure, it's with this definition, it's the same as looking at at v as an fx module, and then looking at the subring f, and the action of the subring f under the fx module structure acting on v is the same thing as f acting on v, giving us our vector space back. So now in general, there are many different fx module structures on a given vector space v, and that of course depends on the linear transformation that we choose, t. So for our first example, if we let t be the trivial transformation, so it sends all of our elements of the vector space to 0, then we get for any p of x, any polynomial, the action of p of x on v is simply going to be the constant term times v, since all the other terms will go to 0. So in this case, with this linear transformation, the trivial transformation, the fx module structure that we get, it coincides exactly with our f vector space structure. So we don't really get anything new from this example. Now, the kind of converse to this, if we let t be the identity transformation, so it simply just maps each element v to itself, then we have that for any p of x in fx, if we apply p of x to v, and we do our same definition here, we apply, we substitute in our transformation, we apply our transformation to v, right? But t to the n, that's the identity transformation, so we just get v back. And we get v back for each one of these applications. So all we're doing really is just adding the coefficients of our polynomial and then applying that sum to v.